Hello, welcome to another video. So in this video, we are going to configure our FPGA board, that is Terasic DE1-SoC board, to run as a VGA controller. So we'll be configuring our FPGA board to run as a VGA controller, where it will generate an image and provide the VGA control signals so that the VGA monitor can run and display the image generated based on the image logic. So here we will first create the VGA interface and then prototype it on the FPGA board, and we'll analyze how it is working. First we'll have a brief understanding of how the VGA works and how the image is generated. The VGA controller logic has three blocks: PLL, the VGA controller itself, and the image source. The PLL makes sure that the board's clock is modified so that it matches the pixel clock required by the VGA controller. So today we are using a 1920 by 1080p display with a refresh rate of 75 Hz. So for that we have calculated what the pixel clock needs to be and its parameters. So here it mentions that we need a pixel clock of 167.85 megahertz. So our PLL will be responsible to generate that. Once that is generated, it will be passed to the VGA controller, which will generate the signals, that is display enable, which is the pixel that we are targeting, respective heatsink and the VSync. So the same signals are also used by the image source to generate the respective RGB values. So as we looked at in the block diagram, the VGA controller generates few control signals, horizontal timing and vertical timing respectively. Horizontal timing signals are responsible to maintain the single line of the image or the pixels that are being rendered, and vertical timing is responsible to control the frame. Here sync pulse is the main thing that controls or notifies the controller that the line is completely generated. We can go to the next line. So once the sync pulse has been detected, the controller will go to the next line and the respective lines after that. And once the vertical sync pulse has been detected, it knows that okay, the complete frame has been generated, we can go for the next frame. So those are the main duties of horizontal timing and the vertical timing. Let's go and see how that is being implemented. In the VGA controller, we have few generic parameters which are defined for the respective display that we are going to use. So mine is a 1920 by 1080p display with a refresh rate of 75 Hz. So based on that, we have few control signals that we'll have to provide. For example, the front porch, the back porch, polarity, and the same thing goes for the vertical signals. So based on that, we have modified these integers, and the module takes in pixel clock and the reset signal and generates heatsink, horizontal sync, vertical sync, display enable, which column and row we are targeting, the blanking signal and the sync signal. So this is the logic that makes sure the sync pulse is read, and once the sync pulse is detected between front push and a back push, it knows that it needs to go to the next line. And the same thing goes for the vertical sync, and once the vertical sync has been detected, it makes sure it goes to the next frame. Once these control signals are generated, the respective image logic also works. So here we are just generating a simple two rectangles on the display. So here our image is just a simple rectangle display on our monitor, where we have a blue rectangle corner to top left corner, and the entire background will be yellow. So in our image generator, we have provided few parameters for the rectangle. We are mentioning that its length or its vertical length needs to be 478 pixel, and its horizontal length should be 600 pixel. So based on that, This module takes in display enable which row and column so that it can target the individual pixel, and it will run the logic. Based on the logic, it will generate the RGB output. So the logic is very simple. If the pixel or the row data is within the vertical pixels, then or if it is within the horizontal pixels, then set the RGB value where red and green are 0 and blue is 1 to get the blue box. Else red and green is enabled where that will generate the yellow square. And then we have blanking time. Blanking time is required to synchronize so that the controller can move to the next line or the next frame. So this entire area where front porch, pulse, sync pulse and back porch exist, so that is the blanking area. We need not send any data over here since this will not be rendered on the display. Only the display time, the data before the front porch, only that will be rendered. So this blanking time is to make sure the next line is rendered or for the horizontal timing, or the next frame is generated for the vertical timing. So this is a simple image where we are just generating two rectangles, one corner to the top left corner and the other which covers the entire background. But to run all this, we need a pixel clock respective for our display. As I mentioned, we are running a 1920 by 1080p display at 75 Hz, and we need a pixel clock of 167.85 megahertz. To generate that, we have a limitation where our board is the limitation. Our board only has a 50 megahertz onboard clock. So our board physically can generate only 50 megahertz. But using that, we can extrapolate higher frequencies. To generate this higher frequency clock, we will use something called as PLL, which will use the onboard 50 megahertz clock signal and generate higher frequencies or any targeted frequencies that we require. So we will go and use the IP modules provided by Intel or Altera. We'll just name it DCM underscore Altera underscore 5. This is just for the sake of showing how the IPs are generated, but here I've already generated the IP. We'll select as VHDL since our whole all our modules are generated in. First, we'll have to provide a reference clock, that is our onboard clock, which is 50 megahertz, and we'll have to disable the locked output ports. We just wanted to generate the clock without any control signals. Desired frequency, we'll have to just mention 167.85. So that is the clock frequency which we have to run so that our display will run at 75 Hertz refresh rate for 1920 by 1080p pixel. And we'll just have to select finish. I'm not going to do that since I've already created that. So once you click finish, it will generate the PLL modules which are responsible to generate the frequencies that we desire. So this PLL will be called in our top VGA module, which will control all the modules. Let us go ahead and program our device. So after compilation, the bitstream file will be generated. We'll just select that and start the programming. So this will use the bitstream and configure our FPGA to run as the VGA controller. As you can see on the display, as soon as the programming is done and our FPGA is configured to run as the VGA controller, you can see on the display a blue rectangle has been rendered on the top left corner and the background is yellow. So this was our image, and the VGA controller using the control signals has displayed this image onto our display. We can also perform some power analysis in our Quartus application. We'll just have to go to processing, power analyzer 2, and this will bring up this window. Here we have few inputs that we can provide here. One is toggle rate, and if you go to cooling solution and temperature, here we can mention some of the parameters that we'll have to use. One is the ambient temperature, what kind of cooling is being used. For our Terasic DE1-SoC board, it has no heatsink and it is just ambient air that cools the chip. So due to that, we'll just select this option, no heatsink with still air, and we'll just provide the ambient temperature. Here we are just providing it as 50 degrees Celsius to see what are the power estimation that it brings up. You just click OK. Toggle ring rate. Now this is the alpha parameter which specifies what is the switching rate of the transistors. Let's click start. So once that is done, it will compile the power details of our design, which we can see in the compilation report. If you go to summary, we can see here the total power estimation, what is the dynamic power, what is the static power, and all the details. So to get a better understanding, we can perform few changes, whether it is in our base clock or our toggle ring rate or at the ambient temperature where it is running. So these are the three factors which broadly define the power parameters. So by varying these three parameters, we'll get a estimation of how the design will perform with respect to power consumption.